Good evening to all of you. Today's our lecture is on eigenvalues and eigenvector. So today we are going to discuss these things. So first of all, raise your hand. Just ensure that my voice is clear or not. Okay, so we are going to discuss today what are the eigenvalues and eigenvectors. So first of all, we are going to discuss definitions of eigenvalue. In the definition, it says that a non-zero vector x is an eigenvector or characteristic vector of the square matrix A if there exists an scalar lambda such that Ax is equal to lambda x, then lambda is an eigenvalue, or we can say characteristic value of A. So sometimes we say that the eigenvalue, or we can say characteristic value. So the zero vector cannot be eigenvector even though A0 is equal to lambda 0, but lambda is equal to 0 can be eigenvalue. So in the beginning, we start a little bit very simple examples. It says that show that x is equal to 2, 1 is the eigenvector for A is equal to this. So a matrix is given A is equal to 2 minus 4, 3 minus 6, and we have to show that whether x is equal to 2, 1 is a eigenvector or not. So what we did here we will multiply a matrix with that vector, and we see when we multiply what we see for lambda is equal to 0, lambda x is equal to this, yani 0 into 2, and we obtain a 0. So thus x is an eigenvector for A, and lambda is equal to 0 is an eigenvalue. So when we multiply it, we get a 0. So that is why we say that it is an eigenvector. So, but we will see more examples. From this more examples we can understand. So it says that let x be an eigenvector of a matrix, then there must exist an eigenvalue lambda such that Ax is equal to lambda x, or we can write Ax minus lambda x is equal to 0. Or we can take x common, we can write A minus lambda I x is equal to 0. So either we can write A minus lambda I x is equal to 0, or sometimes we can write lambda I minus A is equal to 0. So in some books you will see that they are written that lambda I minus A will be is equal to 0. So both into x is equal to 0. So both the things are same. There is no any change. So and this is equation number. This is if we write determinant of A minus lambda I is equal to 0. This is called the characteristic equation. So we have to remember only these two equations. Equation number 2 is for eigenvector, and this equation for eigenvalue. Lambda I, there no one you ask that where we got I means identity matrix. If we multiply any matrix with the identity, we get the same matrix. For example, if we multiply 2 into 1, we get 2. If we multiply 3 into 1, we get 3. If we multiply 4 into 1, we get 4. Similarly, if we multiply any matrix with the identity, we get the same matrix. There is no any change. So this is the property of the identity. So I here lambda I is the identity. So here we say we have to remember two things. Equation number 2 is for eigenvalue, and equation number 1 is for eigenvectors. So these two things we have to remember. So in the question I will show you how we can use these things. So for example, it is example number 1. It says that find the eigenvalue of this matrix. So a matrix is given, 2 by 2 matrix is given, and you have to say that find the eigenvalue. So as I told you, first of all we have to write the characteristic equation. So this is the characteristic equation. Lambda I minus a is equal to 0 is called the characteristic equation. So you have to remember this equation. As I told you in previous slide, if you see, I told you you have to remember this equation and this equation. So we use equation number 2 for the for the eigenvalue. We use this. So lambda I minus a is equal to 0 is the characteristic equation. So when you write characteristic equation, just put lambda minus whatever the diagonal elements in the matrix, just put the lambda minus something, and rest of the elements you put the negative sign. So here we write lambda minus 2 and lambda minus 5, that will be equal to lambda plus 5. And here we have a minus 12, so I write minus 12 will be equal to 12. And here we have 1, so we write minus 1 here. So because of we have a characteristic equation, lambda I minus a will be equal to 0. So we know how we can solve this type of determinants. Just multiply this when we multiply this and then multiply this, so we can open the determinants. So lambda minus 2 multiplied by lambda plus 5, and then minus and then minus 12, 1 to 12, and minus minus become plus, so it will be is equal to 12. So lambda minus 2 and lambda plus 5 plus 12 is equal to 0. Here is equal to 0. So now open the bracket. So when you open the bracket, that will be lambda square and plus 5 lambda minus 2 lambda and minus 5 to the 10. So you will give you that you will equivalent, it will be equivalent to lambda square plus 3 lambda plus 2. So this is a quadratic equation, and it has two roots. Because of it is a quadratic equation 2, so it must have two roots. So the roots are, if you are if you are split them, we can write lambda plus 1 lambda plus 2. So what are the roots of this equation? So this will be is equal to 0. So what are the values of lambda? So you can say lambda is equal to minus 1 and lambda is equal to minus 2. So these are called the eigenvalues. So hopefully you understand how we can find the eigenvalue. So any question up to here, how we can find the eigenvalue of the matrix? So in this way, we can find the eigenvalue of the matrix. So hopefully everyone knows that how we can calculate the eigenvalue. So now these are called, minus 1 is one eigenvalue and minus 2 is one eigenvalue. So the roots of the characteristic equation can be repeated. Maybe it can be repeated like 2, 2, 3, 3, 4. It is possible. It means he says that lambda 1 is equal to lambda 2 or lambda. If that happens, he says that if such type of things happens, the eigenvalue is said to be multiplicity of k. We can say that the eigenvalue is the multiplicity of 2. For example, if the eigenvalue will be 2, 2, so we can say that the eigenvalue is a multiplicity of 2. So in this way we can say that. So if you remember, I solved one type of problems in my face-to-face class where the roots are repeated. So then that's one we can say that the multiplicity. So let's see the other question. It is a 3 by 3 questions, 3 by 3 matrix, and we have to find the eigenvalue of the matrix. And this is a matrix is given, a 3 by 3 matrix is given, and we have to find the eigenvalue. So what we did, as I told you, that first of all we have to find the characteristic equation. The characteristic equation will be lambda I minus a is the characteristic equation. So you have to write this equation. So uh, whatever the diagonal elements, you have to subtract lambda. We have diagonal elements will be 2 2 2. So you will subtract lambda minus 2, lambda minus 2, lambda minus 2 everywhere, yani in the diagonal element. And whatever the rest of the elements, put the minus sign, yani. So here we have a minus 1, here we have a plus 1, we put minus 1, and rest of the places are 0 0. So we put 0 0 0 minus 0 minus 0 everywhere. There is no 0 or minus 0, the same thing, there is no any change. So when you open this determinant, because of everywhere is a 0, so when you open this determinant, you will get lambda minus 2 whole cube will be is equal to 0. You will get this. So what is the eigenvalue? So you can say the eigenvalue of this matrix will be lambda is equal to 2 is an eigenvalue of with multiplicity 3. Either you can say the eigenvalue will be 2 2 2, or you can say that eigenvalue is 2 and with multiplicity 3. So both the things are same, there is no any change. So in this way we can find the eigenvalue. So this is not an eigenvector, this is a eigenvalue. So now next we will see this. To each distinct eigenvalue of a matrix A, there will corresponding at least one eigenvector which can be found by solving the appropriate set of homogeneous equation. If lambda I is an eigenvalue, then the corresponding eigenvector xi is the equation solution A minus lambda I x is equal to 0. So he says that whenever we have, still now we discuss the step number 1. Till now in this example we discuss the step number 1 to find the eigenvalue. It is step number 1. In example 1, it is we again discuss the step number 1 and to find the eigenvalue. This is step number 1. Now we have to proceed the step number 2. So here in example 1, we see that we found the eigenvalue of the matrix. The eigenvalue of the matrix will be minus 1 and minus 2. Let's proceed this example further. So this is example 1. Further we proceed. So as we know that the eigenvalues we found in example 1, that is the eigenvalue lambda will be is equal to minus 1 and minus 2. These are the two eigenvalues we found in previous question. So now we proceed the previous question. So we can write lambda is equal to, corresponding to lambda is equal to minus 1. First, we can found the eigenvector with the, so we apply the formula of eigenvector, that we can write lambda I minus a into x will be is equal to 0. So we can write lambda I, this is lambda I minus a, and in he is not write x, but in my face-to-face class I write lambda I minus a into x will be is equal to 0, will be is equal to 0. So or here they write after that. So we can write lambda I minus a, and means what, where we have a matrix, what we have in the previous slide you can see we have a matrix lambda minus 2. Here we have lambda minus 2. So I write minus 1 and minus 2. In place of lambda, I write minus 1 minus. So we get minus 3. Similarly, in the matrix we have, let's see previous slide, we have 12 here. So there is no any change. We have 12 here, and we have minus 1 here, and we have 4. Let's see in the previous slide. We have lambda plus 5. So lambda plus 5 means minus 1 plus 5. That will be is equal to 4. So this is the matrix is become. So now we can write the matrix in this way. We have a matrix. What is the rank of this matrix? If we found the rank of the matrix will be 1, because of if we see this 1 3 the 3 and 4 3 the 12. So the rank of the matrix is 1, because of you can write with the row operation, you can write the matrix like this in this form. So the rank of the matrix is 1. So we take only first equation. So we take only first equation. So we can write 1x 1 into x minus 4 into x2 will be is equal to 0. We can write in this form. So that's why our eigenvectors are whatever the coefficient, our eigenvectors are 4 and 1. So these are our eigenvectors. So hopefully you understand how we can find whatever the coefficient of this. So the coefficient of x1 is 1 and the coefficient of this is 4. So we can write x is equal to 4tx. So in this way we can write. So that's the eigenvectors are 4 and 1. So similarly, we can find the eigenvector corresponding to lambda is equal to minus 2. In the same way we can write, so we write the formula lambda I minus a into x is equal to 0. So this is lambda minus 2 into I minus a. So I write here, this time is minus 2. So with the help of previous slide, I write the matrix like this in this way, and found that the rank of the matrix is 1 because of only one non-zero rows. So the rank of the matrix is 1. So that's why we take on the first equation, yani 1x minus 3x will be is equal to 0. So that's why our eigenvectors are 3 and 1. So in this way we can find the eigenvector. So hopefully you understand how we can find the eigenvalue, how we can find the eigenvectors. So if you are not understanding, so we have some more examples are there. We will discuss these examples one by one. So any question up to here? Okay, so let's we proceed. It says that find the eigenvectors of this matrix. Recall that lambda is equal to 2 is an eigenvector with multiplicity 2. So this question we solved in previous slide. Like if we see this question, we discussed the example number 2. So find the eigenvalue of this matrix. Then we find the eigenvalue of this matrix will be lambda is equal to 2. Now the problem is find the eigenvector of this matrix. So let's see how we can find the eigenvector of this matrix. So again we will discuss the same thing. So we will be corresponding to lambda is equal to 2. Corresponding to lambda is equal to 2 because of the roots are 2, 2, 2. Or you can say that the roots are 2 in the multiplicity of 2. So multiplicity of 3, sorry. So the roots are 2. So when you put lambda, the formula of eigenvector will be lambda I minus a into x is equal to 0. This is the formula of eigenvector. So lambda I minus a means you will put 2 minus 2, that will be equal to 0. Similarly, 2 minus 2 will be equal to 0. 2 minus 2 will be equal to 0. From the min matrix, you see this. And here is minus 1. There is no any change. Whatever here is plus 1, but whatever the value here, we write minus 1. And rest of the places are 0. Just see in the previous slide, if you remember, this is the matrix. So I write, there is nothing, the same matrix I write here. So, and there is a x1, x2, x3, if there will be is equal to 0, 0, 0. So we are not doing anything. just write in this way. So we can say that x is equal to s. If you solve this you will get x1 is equal to x, x3 is equal to t. So because of when you open this, the eigenvectors of lambda is equal to 2 are, you can write s0t, or you can write 1 0, x is equal to x1, x2 is equal to this, or when you take s outside, there will be 1 0 0, and if you take t outside, there will be 0 0 1. So s and t not both 0. These are the eigenvectors. So there are several properties of eigenvalue and eigenvectors. These properties we have to remember. So just read one by one these properties. So uh, first of all, they say that what is the trace? The trace of a matrix designated by the TRA is the sum of the elements of its main diagonal. So this question is appear in the midterm in this time. If you remember, it says that what is the trace? Trace means whatever the element in the diagonal, if you add them, that is called the trace of the matrix. So now there are several properties. The property number one is the sum of the eigenvalues of the matrix is equal to the trace of the matrix. Whatever the trace of the matrix is equal to the sum of the eigenvalues. So this is one property. Property number two, it says that the matrix is singular if and only if it has a zero eigenvalue. Property number three, it says that the eigenvalue of upper triangular matrix or lower triangular matrix are the elements on the main diagonal. So there is this type of question I solve in my face-to-face class. If you remember, if we have a matrix, either it is lower triangular or upper triangular, then the eigenvalues are its main diagonal. Similarly, if lambda is an eigenvalue of A and A is invertible, then 1 upon A is an eigenvalue of a matrix A inverse. So these are the properties. These are helpful for us. And similarly, if property number 5, if lambda is an eigenvalue of A, then K lambda is an eigenvalue of Ka, where K is an arbitrary scalar. So, and property number 6 is if lambda is an eigenvalue of A, then lambda to the power K is an eigenvalue of A, K for any positive integer. So, similarly, if lambda is an eigenvalue of A, then lambda is an eigenvalue of A transpose. The product of eigenvalues counting multiplicity of matrix is equal to the determinant of the matrix. So these are the properties. These are helpful when you are solving, when you are trying to solve the questions, or when you are solving the examples. So there are some more linearly independent eigenvectors. These are some more explanations are given. What are the eigenvalue problem? It says that if A is an m cross n matrix, do there exist a non-zero vector x such that Ax is a scalar multiple? So if A is a n cross n matrix, a lambda is a scalar, x is a non-zero vector, then Ax is equal to lambda x is, so x is an eigenvector and lambda is an eigenvalue, x is an eigenvector. So by geometrical interpretation, we can represent like eigenvalue like this. So these are some more examples are there, verifying the eigenvalue and eigenvector. So if there is a matrix and there are two eigenvectors are there, they say that just to verify them. So when we multiply Ax, that will be is equal to 2 0. So when you take a 2 outside, there will be 1 0 is here. So again, this is an eigenvector. So it is equal to 2x1. Similarly, again, if you multiply 2x2, then 0, 1, if you multiply any matrix with the eigenvector, so that will be 0 minus 1. Take minus outside, that will be 0 1. So again, we will get the same thing. So these are the steps for your understanding. So this is a very simple question. It says that find the eigenvalue and eigenvectors of the matrix. So it is a 2 by 2 matrix. Find the eigenvalue. So first of, as you know, we have to write the characteristic equation. The characteristic equation will be lambda I minus a will be is equal to 0. So we can write lambda minus 2 and lambda plus 5. Just wherever the diagonal element, we can subtract lambda. So we write that lambda minus 2, lambda plus 5, and rest of the element is 12 and minus 1. So it is a quadratic equation. The roots are minus 1, minus 2. So these are the two eigenvalues. Lambda is equal to minus 1 and minus 2. These are the two eigenvalues. Now find the eigenvectors corresponding to lambda is equal to minus 1. After that, we will find the eigenvector corresponding to lambda is equal to minus 2. So corresponding to lambda is equal to minus 1, when we write this, that will be is equal to lambda 1 I minus a x is equal to 0. So we can write lambda 1 I minus a into x is equal to 0. So that will be is equal to, I will subtract. So in previous slides, you see that in place of lambda, I will put minus 1. So minus 1 and minus 2 will be is equal to minus 3. So I write minus 3 here. And the rest of the thing is 12 here. I write 12 in the previous slides. The 12 is here. So there is no any change. And there is a minus 1 here. So minus 1 here. And similarly, minus 1, and that will be is equal to 4. So, and into x, it will be equal to x1, x2 will be equal to 0, 0. So we know that we have whatever the rank of the matrix is 1. So we solve only one equation. So we can write 4t, or t is a variable. We can take 4t and t. So if we take t common, we have a 4 and 1 is outside. So we say that the eigenvector will be 4 and 1. Similarly, corresponding to lambda is equal to minus 2. We have to find the eigenvectors corresponding to lambda is equal to minus 2. So let's see that how we can find the eigenvector corresponding to lambda is equal to minus 2. So that will be equal to lambda 2 minus a into x will be is equal to 0. So you have to put the value of lambda 2, that is minus 2, and we in the previous slide, if you see the main matrix, minus 2 and minus 2, that will be is equal to minus 4 here, and the 12 is same here. There is no any change. Minus 1 is same here. And what about in the previous slide, you will see the lambda plus 5. So lambda plus 5, we have a lambda minus 2 and plus 5. So what you get, minus 2 plus 5, you will get minus 2 plus 5, you will get a 3. So you write 3 in place of this. So you will write 3 in this place. So and x1 and x2, that will be is equal to 0. So again, the rank of this matrix is 1. So that's why we choose any one row, either row 1 or row 2. So we choose any one row and take. So we write 3t and t, and that will be t is outside. So 3 and 1 are the eigenvectors of this matrix. So hopefully you understand the concepts of eigenvalue and eigenvectors. So anyone confusion, if you have, then ask me. So now let's proceed. Some more examples are there. It says that find the eigenvalues and corresponding eigenvectors for the matrix A. What is the dimension of eigenspace of each eigenvalue? So a 3 by 3 matrix is given, and you have to find the characteristic. First of all, we have to find the characteristic equation and then find the eigenvalues of the matrix. The characteristic equation of the matrix will be lambda I minus A is equal to 0. This is the characteristic equation of the eigen of the matrix. So lambda I minus A will be is equal to 0. It means we can write lambda I minus A will be is equal to 0. We can write lambda just everywhere we will subtract lambda. So we have lambda minus 2 and lambda minus 2 and lambda minus 2. And here we have a 1, so we write minus 1. So when you solve this, we will get lambda minus 2 whole cube will be equal to 0. So our roots are lambda is equal to 2, 2, 2. We have the repeated roots are there. Or we can say that we have a root 2 in the multiplicity of 3. So eigenvalues are lambda is equal to 2, 2, and 2. Here they write only 1, 2, but we have to write 2, 2, and 2. So these are the three eigenvalues of the matrix. So now he says that what is the eigenvectors of this. So as you know that the eigenvector, the formula of eigenvector will be lambda I minus A into x will be is equal to 0. So lambda I minus A, so that is yani 2 minus 2 will be is equal to 0. 2 minus 2 will be is equal to 0 and 2 minus 2 will be is equal to 0. So rest of the things are same. So that will be is equal to x1, x2, x3. So these are the, so when you see this, you will multiply this x1, x2, x3, this will be equal to s0t, or if you take s outside, 100, and t outside, that will be 001. S and t are 10. So this type of question we solved earlier. So again, find the eigenvalues of a matrix of A, find the basis for each corresponding eigenspace. So this we can also solve like this. If here we have a 4 by 4 matrix, 4 rows, 4 columns, so there is no any problem. We can solve this type of matrix again. So we just open the bracket. We can find there is a the value of the eigenvalue will be lambda 1 is equal to 1, lambda 2 is equal to 2, and lambda 3 is equal to 3. So we can see this type of questions. So you will see. You will give you 1 minute. You will watch clearly how we can write this type of equations. How we can write these equations, how we open this determinant. There is a very big determinant how we can open this determinant. So it's very simple because of all the elements are 0, 0. So we can easily expand this determinant and we will get lambda minus 1 squared, lambda minus 2, lambda minus 3 is equal to 0. So after that we will proceed, and up to you will watch, you will see this how we can solve it. can see this or eigenvalues are lambda 1 is equal to 1, lambda 2 is equal to 2, lambda 3 is equal to 3. These are the three eigenvalues of this determinant. So now we proceed every one by one. First of all, we will find the eigenvector corresponding to lambda is equal to 1 because of we have three eigenvalues. So first of all, we find the eigenvector corresponding to lambda is equal to 1. Then we find the eigenvector corresponding to lambda 2 is equal to 3. Then we find the eigenvector corresponding to lambda 3 is equal to 3. So one by one we find the eigenvectors. So for 1, lambda is equal to 1, the eigenvectors corresponding to lambda is equal to 1 will be lambda 1 lambda I minus ax is equal to 0. This is the formula for the eigenvector. So we can write lambda 1 I minus 1. So 1 minus, if you see in the previous slides, so 1 minus 1 here, 1 minus 1 will be equal to 0, and 1 minus 1 will be equal to 0, and 1 minus 2 will be is equal to minus 1, and 1 minus 3 will be is equal to minus 2. So just see in the next slide, that will be is equal to 0, 0, minus 1, minus 2. In this way we can write. So similarly, we see this. This is our whole. We write every element. Now there is x1, x2, x3, x4, and there is a 0, 0, 0, 0. So now we can write that will be equal to just take and just open this and we can write. So that's in this way, because of the first row will be 0, 0. So we can write in this way minus 2t s and 2t and t would be equal to, if we take s outside from s, if we take outside, so that will be equal to 0, 1, 0, 0, and if you take t outside, then we'll take minus 2. So in this way we can write the eigenvectors. So is a basis for the eigenspaces of A corresponding to lambda is equal to 1. So in this way we can write a basis or eigenvectors. So corresponding to lambda 2 is equal to 2, we can also write this. Similarly, corresponding to lambda is equal to 3, we can also write. In this way we can write the basis for this. So in the eigenvalue of a triangular matrix. So if A is an n cross n triangular matrix, then its eigenvalue are the entries or its main diagonal. So this is the property that we show. This is the theorem, and we solve this type of question in my first class. So here it says that this is a matrix is given, and you have to ask the question, find the eigenvalue, and this type of question is appear only in 1 mark. So why? Because of, and this is a very big problem, and this big problem appear only in 1 mark because of the answer is only 1 line. So you have to ask the question, find the eigenvalue of this matrix. So you directly put the eigenvalue of this matrix will be its diagonal elements. That is, lambda 1 is equal to 2, lambda 2 will be equal to 1, lambda 3 is equal to minus 3. There is no need to solve in this way like this. There is no need to solve like this in this way. You directly put the answers in this way. So because of, you can say that by the theorem, it says that whenever we have a triangular matrix, either upper triangular or lower triangular matrix, the eigenvalues are its diagonal elements. So that's why we put the answers. Similarly, there is another problem, B type of problem. It says that there is a matrix is given here, and you have to ask find the eigenvalue of this big matrix. So there is no need to solve a big matrix. Just see what are the diagonal elements are there in the matrix. So the diagonal elements are these are the diagonal elements minus 1, 2, 0, and 3. These are the diagonal elements. So you put lambda 1 is equal to minus 1, Lambda 2 is equal to 2, lambda 3 is equal to 0, lambda 4 is equal to 4, and lambda 5 is equal to 3. So these are the eigenvalues of the matrix. So there is no need to solve further. So hopefully you understand how we can solve the eigenvalues of the triangular matrix. Okay. So now let's next we proceed. So the last topic is diagonalization. So it is a little bit long, diagonalization. So here the definition is says that for a square matrix A, there exists an invertible matrix P such that P inverse AP is diagonal. So we have to find P inverse AP. So, so let's see an example. With the help of example, we can understand what is the meaning of how we can find the diagonalization. So it says that this is the example, and it says that diagonalize the matrix. A matrix is given 3 by 3, and you have to you have to diagonalize it. So in diagonalization, just keep in mind we have 3 steps. In step number 1, we have to find the eigenvalue. See, first of all, we have to find the eigenvalue. In the second step, we will find the eigenvector. And the third step, we will find the P. What is the P? P is the combination of all eigenvectors. So we will find P. And the fourth step, we will find P inverse. And the fifth step is we will find P inverse AP. The fifth step is we will find P inverse A into P. So there are 5 steps. In these 5 steps, we can convert into diagonalizable matrix. So let's restart. We have a 3 by 3 matrix is given. We have to find the eigenvalue. So the eigenvalue of the matrix will be lambda I minus A will be equal to 0. As you know, we solved so many examples before. So we can write lambda minus 4, lambda plus 2 whole square will be equal to 0. So what are the roots are there? So the roots will be equal to lambda is equal to 4, and lambda is equal to minus 2, and lambda is equal to minus 2. So these are the roots of this matrix, or we can say these are the eigenvalues. So our step number 1 is complete. Now move to step number 2. We have to find the eigenvectors. So corresponding to lambda is equal to 4, then find the eigenvector corresponding to lambda 2 is equal to 2, then find the eigenvector. So corresponding to lambda is equal to 4, the eigenvectors we found, we are not explaining here, directly we found the eigenvector would be 110. Let's we say it P1. Similarly, find the eigenvector corresponding to lambda is equal to minus 2. Let we see it P2, and corresponding to minus 2 again, let we see P3. So combine all P1, P2, P3. So here, combine all P1, P2, P3. We call them a P. So combine all these, we will say that this is a P. So now, after that, we find a P inverse, and after P inverse, we multiply all these 3. We get P inverse AP is equal to this. This is a matrix. So, this is called the diagonalization. Because of it is a long process, that's why this type of questions are very long. So maybe in this long way maybe not appear in the exam, but some type of in the main question there's some small parts maybe asked in the question. So that's why in this way we can solve AP inverse AP. So again, he say that show that the following matrix is not diagonalizable. So in the same way we can solve this. So it is the end of today's lecture. So if you have any query, you can ask me. If you have any question, then you can ask me. Yes, your answer is what is lambda? Lambda, everything is I told you everything, and at the last you asked that what is lambda. Lambda is any scalar. We found the value of lambda every question. We found the value of lambda. So any whatever the value, these are the constants. When we solve that, this you, if you are not saying that lambda, you say that it is x. So x minus 1, x minus 2, x minus 3, x minus, so there is no way. So this is like a constant. So here we found it is a scalar. So we found the value of lambda. Lambda is equal to 4, lambda is equal to minus 2, lambda is equal to minus 2. So in every matrix we find the value of lambda. So like we see, if you see in the previous slides, in every question we found the value of lambda. So for example, here we have a 2 by 2 matrix. So we write a characteristic equation in this way, and we can write lambda square plus a lambda this, and after that we find this value lambda is equal to minus 1 by solving this. So whatever the value of lambda, that is called a scalar. So if you are not interested to take lambda, then you can take any other value like a b c or x y z. So so it is called the lambda. There is yeah, don't confuse with any. This is a type of variable. For example, we say that x y z. So here we say that lambda. So so there is no need to be confused. Okay, any other question? How do you get P1? So P1 means the eigenvector corresponding to lambda 1. So the P1, whatever the eigenvectors, we say that is called the P1. So here, this is the eigenvector, eigenvalue. These are the eigenvalues for one. So corresponding to this eigenvalue, we get an eigenvector. So this eigenvector is called a P1. So 110. In the previous slides, we found that how we can find the eigenvector. So in the same way, we can find the eigenvector like this. So there are 2 or 3 steps or more. We can find the eigenvector. Here I'm not explaining. So in the previous slides, you'll see that how we can find the eigenvector. So this is the eigenvector of corresponding to lambda is equal to 4. Similarly, we can find the eigenvector corresponding to lambda is equal to minus 2, then minus 2. So if you see that eigenvector can be found in the previous slides, you can see how we can find the eigenvectors. For example, this is, if you see, this is 2 by 2 matrix. Here these are the eigenvalues. Now let's see how we can find the eigenvector. So this corresponding to lambda is equal to minus 1, we can find the eigenvector, this 4 and 1. In this way, you can find the eigenvector. This is called the P1. Similarly, this is called the P2. So in this way, you can find the eigenvector. So okay, so just read it, um, these PowerPoint slides again, again and again, so you can understand this. So P inverse can be found if you see that the inverse formula will be there is a one. You write the identity matrix here, and then 0 0 1, and then after that you will write your matrix here, matrix whatever the matrix you write here, and after that you will convert this matrix into the identity matrix. Whatever the matrix you will get on the left hand side, that is called the inverse. If you remember, in the week we teach we read these things in week 4 or week 5. So in this way we can find the inverse. So, okay, so you read it and you can understand if you read it clearly. So, okay, yes, that's why I'm saying you that will be the long process, because of the inverse. Finding the inverse is a little bit long. So okay, have a nice day, and just do work hard.